This is Swarfcast. I'm Noah Graff. We are live from IMTS with Steve Vanderink and Bryan Stusak from Iscar. Welcome to the show, guys.
Thank you, Noah. Appreciate it.
These guys were schooling me on cutting tools today as I wandered into their cool booth, one of the better booths at IMTS for sure. And we're going to talk about cutting tools and specifically small parts, and just going to find out the nuances of tooling. So first, before we go any further, just why doesn't one of you just say real quick what Iscar is for people who don't know? Probably a lot of the listeners know who Iscar is, but let's give them a little context, and then you can just tell us quick who we are, and then we'll go into some education.
Sure, I'll do it, Noah. So Iscar has been around. It had its 60th anniversary in 2012. Family-owned business, but it's a full-line supplier now. We were the first in the market with a self-grip pressed carbide insert. And so Iscar is known for its innovation. It's known for killing its own product, as Steph Wertheimer would say. And he was the founder of the company.
Right.
So innovation in every phase of the game is what we're driven by, Jacob Harpaz and the Wertheimer family. And so innovation, and also the support in the field is what it's known for. And that's really the best I could describe it, where innovation never stops on all the buildings in our tech center in Tefan, Israel, where we're located at. So
they still make the cutting tools in Israel?
They certainly do. It's worldwide manufacturing because the market demands that, but that's where the main plan is at.
Very cool. Is the cost of labor high in Israel?
It is. It's very high. And of course, you have logistics costs too, right? Mm-hmm. But that's the way of the world. I mean, manufacturing has to be done where it's consumed in a lot of phases, you know. So I think it's important.
Do you have anything to add, just summarizing Iscar?
Well, again, we're a global company, so we're located in every continent of the globe. So,
what do people use the tools for? What kind of machines? Give us like the 5-year-old explanation of the company.
Well, if you think about it, you know, everything is made somewhere and somehow. So we are a company that has designed and engineered metalworking cutting tools. So the carbide substrates, which is what is the predominant, I would say, material used to form cutting tools, whether it's milling, turning, or drilling, is used to manufacture all the widgets that we take for granted every day. Anything from automotive to aerospace to medical, power generation, heavy industry. So everything that we touch for the most part and look at has been touched or machined by a cutting tool.
Okay.
And whether it's carbide, it could be ceramic, it could be PCD, which is diamond, or CBN, which is a man-made form of diamond, to manufacture various materials that make up what we use on a daily basis.
Okay. So, obviously, I mean, our audience, they're in precision machining. You know, they know the basics. What do you think is, you know, a hole in people's knowledge with the cutting tools? Why did you suggest to me that we talk about small parts manufacturing in the first place?
Well, when you think of...
And how small are we talking? Are we talking like 5 millimeter? Are we talking like dental implants? Or are we talking... Yeah, what are we talking?
In every industry segment, there's smaller components being made on Swiss-style machines. BT30 robo drills, which is a milling machine. A lot of these components demand smaller tooling. Okay, and most of the tooling used from a milling standpoint, because I'm the milling product manager, is carbide end mills. Okay, so when we think of from a milling standpoint, excuse me, you know, what is the trend? What are we looking at in the future? a lot of the companies now coming on board, especially at IMTS, is additive manufacturing, 3D printed components, near net shape forgings, castings. So very little material is going to be removed at some point going forward. And we've developed on purpose.
Why is that with those kind of products? Why would not very much material be removed? Because it's already almost to the right shape, I guess.
Right. So these components that are 3D printed are printed, manufactured in that process to almost its complete shape. And because of how unstable that process is at this point in the game, certain features of a component have to have machining done on it.
Yes.
For tolerance reasons or locating purposes. So very little material's got to be removed, as opposed to what we've seen in the past where you have a block of material that has to have a lot of metal removal to get to a final shape.
So I guess at first thought you'd think, all right, you don't have a ton of material to remove, you just have a little bit. I think that would be easier than if you have just a block and you start chipping away at it. But my assumption is it's sort of its own art, doing that.
Well, I want you to think about this. With COVID affecting the supply chain channels and getting materials, the cost of materials are going up. It's actually forcing a different mentality in the industry. Because of cost. And so why should you develop a product that has to have all this machining done on it, which is labor and time and cost, when you can 3D print a component and finish machine certain features? And that's what we've developed. We've developed indexable products in relationship to solid tools like end mills to be able to machine those features and save the end user some money, the manufacturer some money.
Right, but I guess my question is it easier to remove a little bit?
Of course it is.
Shave off a little bit than a lot?
Of course it is. It's less time, less wear on the cutting tool. You're not going to be buying as many cutting tools because everything's about contact time with the tool and the workpiece material. The more time that the tool touches the material, it's going to wear out quicker. And so if it wears out quicker, you got to buy more tools. So is
that bad for Iscar's business then?
It's changing our thinking.
Yes, it's changing what we design, as Bryan mentioned. So the tooling looks different. The mills that we're making now, the smallest insertable mills in the market, Iscar is developing now because of that change in the market. Yeah. Because of that. So is it hurting us? Well, maybe volume, maybe because we're not hogging out a bunch more material in a general sense. But we're changing in typical Iscar fashion. We're changing the way we produce and what we produce to fit the market's needs. So it's well put. We're changing the types, and you could segue right into the turning side on the Swiss type machines that are small parts. They're near net shape.
How small are we talking?
Well, it could be a needle, as small as diameter as a needle, right? Just that small. So you could say that the parts done on a Swiss machine are near net shape, right? There's not a lot of material coming off. Maybe the material that you're using, the rough stock, is maybe 3/8 of an inch. Not a lot, but it's inherent with the products that you're making. Maybe an aircraft rivet, maybe a needle, maybe some sort of a bone screw that goes into your mouth. Those aren't big components, right? So those are small, near-net shaped components, even though they're being made out of solid stock. It's just the nature of what's being manufactured on a Swiss machine. Now, I will say this also, that the Swiss market is growing because there's such a large demand and it's increasing for those difficult machining materials, which is good for medical and aerospace, right? It's not easy stuff. You don't see a lot of carbon and alloy steel components being made on Swiss machines. It's just not inherent with those types of parts needed, okay? So the tools needed for that are very specific. And because of the manufacturing dynamic and the need, quick change tooling now, I could get into the specifics of submicron grades of carbide that are needed for those types of materials. The fact that you can't run at high surface speeds because the diameters like a needle are very small. You can't run at high speeds. You need a very tough grade of carbide. Very specific and sharp tooling, okay? But now, not only that, the industry is demanding quick change and super accurate.
And you're seeing that on the machines. They're doing various new features to make it easy to change it fast.
Nowhere in the market, that's a very good point. Nowhere in the market do the days of just having a lathe with one turret, in speaking of our line, you know, one turret turning apart and cutting it off and then doing another operation, those days are gone. Now, some people are still there, but they're always looking for sub-spindles to pick off. They want a complete part coming off that machine. So Swiss machines specifically, and there's a lot of them out there, they complete a very difficult part, very long, very small diameter, difficult to machine, complete.
And why is this? Why is this? These cutting tools, why are they easier to change over?
Well,
tell me about the design. Maybe you can show it on
well,
camera.
there's great repeatability because of the locating surface, very high precision surfaces that are machined, and you can see from this particular design.
Try to show it.
In our Neo Swiss, you have a very robust hook, so to speak, but it's a locating surface that's actually, it's a rotating clamping system that sucks it in and clamps it very securely. So even though it has to be exact, it has to be very robust. And it's very, very important that we have indexability, that when you have changeovers or you change an insert, because of the exact tolerances in these particular industry, medical, dental work, things of that nature, aerospace, it has to be robust, and it's very critical that it's rigid, because it's very critical. The materials you're cutting are very difficult to machine.
So to add what Steve is saying, if you take that head, it's multiple heads of different insert shapes for different applications. The repeatability of that head into the shank is 4/10 of an inch. So what does that tell you as a user? I do not have to have as skilled labor to be able to take that tool and measure it from changeover to changeover or insert to insert. No different than milling. You know, we've had since the year 2000 the quick change system called Multimaster, which is a screw-on modular head of carbide of a particular shape for a given application that screws into a shank, and the repeatability of it being 4/10 is the same. So what that does, it allows you to quickly change out inserts without having to measure, and it keeps the spindle running. Okay, so that's the key. If we can keep the spindle running, we're making money, we're making chips. And so Iscar in the year 2000 developed Multimaster, and it's over 50,000 combinations of different insert shapes.
Does anybody else do this, or is it patented? Or
we do have our competitors that have copied this design, and it's not exactly like Multimaster, but it is a quick change system. So they saw how wise that design was, and certainly jumped on board, and you know they're following Iscar.
I'm gonna go backward, just go off on a tangent for a second. What exactly is carbide? How does carbide? I mean, when did it come about? How do you make it? I know this could be a long explanation. Give me like the 1-minute explanation of carbide. Every tooling manufacturer says they have carbide tools. Give me the cheat sheet on it.
No, I'll tell you this. Carbide has been around for 100 years. In fact, I want to say the Germans invented it, okay? What it is, it's a tungsten powder mixed with a binder or glue like cobalt, or cobalt is the binder. And so when you mix the two and you compress the powder into a die set or a mold of the shape of the insert, and take that insert out, which is in a green state, and you put it in an oven and you bake it, it hardens to what you see today. And so that hard metal, that tungsten carbide, is harder up to 80 plus Rockwell than the material you're cutting. Therefore, it's able to shear the material. It can withstand a lot of heat. And with modern coatings now, PVD and CVD coatings, which is like a paint that goes on a surface, it's actually protecting the substrate, which is the raw carbide. And so that allows
the whole tool isn't made of carbide. The tool is made of metal and it's coated with carbide.
Well, no, it's not coated. The tool, like this insert here, is solid carbide.
Oh, okay.
This shank is made out of tool steel.
Okay.
Maybe an H13 or something like that that's very tough.
And so when you look at this little milling cutter here, the shank here is made out of H13 tool steel, hardened, okay? And these little inserts are carbide. And so you're able to index to one edge after another and replace the carbide after it's wore out. So the durable is the shank.
Okay. Good. Now we can get back to what you were talking about before. So what are the things that people don't, the real holes in people's knowledge about this subject of making the small parts? Okay, so now we know how they've improved, quicker changeover, that helps people that are less skilled set the machines up. What are the holes in people's knowledge? What are you seeing when you go to a shop that people are getting wrong?
I'll take that on. From a milling standpoint, what we see is a very common, I wouldn't say a problem, but a concern is the fact that people are still using solid carbide end mills to machine features at very shallow depths of cut. So when you think of Swiss-style machines, whether you're cutting hex flats, doing any shoulder milling, slotting, it's typically very shallow on a small component.
Just like you were talking about with 3D printed stuff, it's shallow.
It's shallow, so it does not make sense to use a solid carbide end mill with X amount of flute length and only use the tip of the tool. And then once you wear that tool out, you're going to do two things. You're either going to regrind that end mill or you're going to toss the carbide. And if you toss that carbide, you've got a large portion of the cutting edge that you bought that you didn't use. And so what Iscar's done...
So they're still doing an okay job. It's just they're wasting.
They're wasting their money and they're wasting resources. And with the commodity prices going through the roof, like gasoline, carbide, everything under the sun because of what COVID has done, we got to change our thinking if we want to be productive and profitable in our machine shops. Because part of the equation in the CPU equation is the cost of the tool. Of course, your biggest savings...
Isn't that bad for Iscar if people are buying less because they're, making less waste?
Well, the bottom line is either we educate people and try to help them save money and innovate new products,
or somebody else will do the right thing.
That's right. And like Steve had mentioned, we're an innovative company. Always have been, always will be. It's the Israeli mindset. They're looking 5 years down the road of what we can be, and typically we're copied. Down the road, you'll see many copies of our products.
And everybody else says that they're copied as well.
Well, that's what everybody copies everyone to some degree.
Sure.
You know what I mean.
Yeah. No, I mean, and you guys, I'm sure you're different from the others in your own respect. And look, I'm a fan of Israel. I'm Jewish. I don't doubt they're the best. Sorry, everybody else. So, okay, people don't know about they're wasting material because they're not using the proper amount of carbide on their tools. What else? What are people getting wrong?
Well, I think that sometimes that they're defaulting to maintain rigidity, they're using tooling that's too big. Like, let's speak about parting off. Now we're talking about, because of the innovations in clamping and the styles and the way we're holding inserts now, we're able to use a much thinner insert with parting off, wasting much less material. Listen, parting off on especially the Swiss machine is a last portion of the job for that operation. And now we're able to, with just a few of the innovation like the Swiss grip, able to go down to 24 thousandths wide. So what does that do? Exactly what Bryan spoke about. We're able to part off parts now that are very, very small, that you wouldn't need a 2 millimeter wide part off, which is very popular in Swiss machines. Now we can go down to 24 thousandths or 30 thousandths wide and still have a great quality part, get coolant right to the cutting edge. So sometimes they're thinking, well, I have to go with bigger to maintain rigidity. Not the case anymore because of innovative clamping. Yeah.
Interesting. Well, what are some of the other things you've brought with? And we can talk about it.
For example, let me pull this up.
To be very descriptive for all the people just listening. But
when you think of end mill diameters, smaller diameter end mills like a quarter.
We got all kinds of toys here because we're at IMTS.
A quarter inch, is pretty small for a solid tool.
Put it up on here.
What we're looking at here is the world's smallest indexable feed mill.
Okay.
So this indexable feed mill, called the NAN mill, goes down to 5/16 of an inch in diameter, 2 flute effective. Now, what's interesting about this design, this is a triangular shaped insert. You notice that the insert...
This is an enlarged version.
Yeah, this is an enlarged version to kind of give you an idea of the design. This triangular shaped insert has a trapezoidal faceted design on top of the insert that simply allows the screw to dovetail the insert into the pocket. So most of the time you would see a insert screw go through the center of the carbide to clamp it in place. In this case, it would make the carbide too weak. So with this design, it's a lot more user-friendly than having to back the screw completely out of the cutter body to index the insert. You simply loosen the screw, and on the wrench that comes with the product, it's got a magnet on it. And so the magnet allows you to pull the insert out of the pocket, and you simply rotate it to a new, fresh cutting edge. And what's nice about this product is the fact that you have a cost per edge advantage over a solid tool.
Sounds pretty useful.
It's saving the company money. Think about this. I wear that edge out, I index it, I get 2 more cutting edges. You wear out a solid carbide feed mill, you're not going to regrind it because the geometry on the end is too complicated. You're going to toss it. So you've purchased a long piece of carbide with a geometry that's designed very similar to what we see here, and you're wasting your money. With this, you have indexability, cost per edge advantage. You also have the fact of numerous insert grades. When you think of carbide end mills, it's typically made out of a micrograin carbide with a 10% cobalt content. It's very hard. So with this, we have that same technology in inserts, very hard grade for wear resistance, but we also have bubblegum grades, very tough grades to allow you to have nasty interrupted cuts, long reaches. Where you have vibration problems, this withstands it. So indexable, it's got its fit. Again, you have a little bit more flexibility with a steel shank. We have this design like we saw here earlier with a multi-master connection. We also have this design with a multi-master connection integral with an ER collet system, ER11 all the way to ER40, which allows you to get the gauge length very, very short for stability. So when you think of the mini mill overview, we have 3 families, the Healy 3 mill, the Healy 4 mill, and the NAN mill. We offer that not only in 90-degree shoulder milling configurations, but feed mill configurations with shallow depths of cut for those near net shaped designs.
And shoulder milling is where you're cutting the side of the part.
That is correct. So this is an example. This is the Healy 4 mill. This is a quad-shaped insert with 4 indexes on the insert. So the lead angle here is perpendicular to, or I would say parallel to the shoulder. So it allows you to create a 90-degree shoulder. You can face with it, shoulder, side plunge with this particular product. Designed for your common milling applications as opposed to feed milling.
Okay. Show us a little bit more. What do you got?
Right.
What do you got?
Let's see here.
Got all kinds of good toys here.
Next product is the Healy 4 mill overview. All right, there we go. So what you have here, the Healy 4 mill, for example, this is the multi-master connection we talked about. We encourage this design versus a steel shank that's integral. Why? Because these inserts and the insert screws are very, very small. And so they can be challenging to deal with. So it'd be better off if you had multiple heads, one in the spindle making chips and another one offline, where you can manage the inserts and screws close at hand with your eyes on a bench. So again, multi-master connection. This family here comes with a quad-shaped insert with 4 indexes for square shoulder milling. And it also has a feed mill insert that can go in that same pocket. So the versatility of this design is pretty enormous. So you can fast feed with this product at shallow depths of cut with very aggressive ramp angles, very aggressive feed rates, and also square shoulder with it at the same time. So very versatile. This comes in diameters starting at 3/4 down to 3/8 of an inch. The NAND feed and the Healy 3 mil family, I believe, come in diameters from 5/16 up to 3/8 of an inch.
Do you have anything to add?
No, if you're starting to hear a theme that I'm going to springboard off what Brian's talking about, versatility, right? Different inserts that fit into the pocket. So there's a nice segue into some of the tooling that's used on Swiss machines in the Neo Swiss line that we showed just a little bit earlier here. We have a family of heads that kind of goes off that same thing where you keep the shank inside the tool post, and now you have versatility, as Brian mentioned, versatility going to the different operations as you segue from job to job seamlessly and accurately.
Right.
That's the key.
Going from job to job.
Absolutely. Right. So it's as you look at it, talking about repeatability now, I'm going to need you to hold my microphone as I pull.
Whoa, cool. Describe to the listeners what we got here.
So what you have is a typical setup for internal working inside of a small part. You know, we've been talking about outside diameters, turning the OD of a part on a Swiss machine. Here we're looking at internal type holders that hold very small tools that do the inside, okay? In holes.
How small of tools?
Well, you're looking at, we can get inside a 30 thousandths diameter hole to do some ID grooving and boring. That's how small, okay? So that particular example is sitting here in these holders, but that's typically what we do here. So when you get to that small, it's so small, as Brian mentioned in his insertable mills, we get down to 312 diameter, the small size, the smallest one out in the market. This is so small here where we don't have the room for insertable tools, so we go to solid carbide. Okay, so in the Swiss world, it's so important to have the design. All of our tools, including the milling tools, if I may say, are built with cooling through. In today's industry, cooling through right at the cutting edge, right? Should be, okay. And not only is it, you don't need to have high pressure coolant. We have found, and we tell our customers,
So it just comes right through the tool.
it comes right through the tool, and in this case, not just splashing on it from a distance, it comes right at the cutting edge, right on the cutting edge. All of our tools, if you look at our coolant orifices, are positioned so it comes right on top of the insert. It makes a big difference whether it's high pressure or not, okay? In this particular instance, the Pico cut, the Pico Jet.
Can the tooling affect whether you need high pressure or not, or is it basically this job needs high pressure?
Well, it should be used in every case. That's my advice. That's
High pressure coolant should be always?
Yeah, absolutely.
Yeah, let me add to that.
All right, well, that's a tip for the podcast.
Absolutely.
Well, think about this. If you take a garden hose, you turn it on, and you put your thumb over the end, you feel an enormous amount of pressure. And as you move your thumb off the top, you see that jet stream of coolant coming out. What high pressure coolant does is act as a hydraulic wedge to the chip and rake face interface to help lubricate the cut and curl the chip away from the cut zone. So if you can cool the cut zone down more than usual, you can elevate your cutting data to get more productivity. That's why we encourage through coolant on every application.
Well, there's through coolant, and then there's
A high pressure.
High
excuse me.
pressure. So whether you're doing tiny parts or large parts, always high pressure coolant.
Well, we used to be called Jet HP, but it's coolant through holders. It doesn't have to be. It's not necessary. Hey, I'm not going to get coolant through holders because I don't have high pressure.
Well, okay, yeah, go on.
No, but it makes a difference in either case. It's either case. So when you have machines with high pressure cooling capability, 1,000 PSI, let's use that as an example.
Yeah.
Okay, some people may not purchase that on their machines. It's not death. We're just saying that all of our tools, it's a benefit to have that option available in all of our tools. Even if it's not high pressure, it will benefit you. I hope that's accurate. I think
That
it's
is correct.
And so,
But what you said before is, if you had a machine, you'd always buy high pressure.
Yes,
Absolutely, I would.
Absolutely.
Is there a certain material it's less important on?
well, yes, it's a good.
Is it small diameters it's less important for, or?
No, absolutely not. But what typically it's the material that dictates it. But I think Brian would agree with me. Carbon and alloy steels, it's not quite as important, and and then your alloying, your cast irons and things that create their own chip. Not so much important, okay? But high temperature alloys and things of that nature where the chip does not get in, the heat does not get into the chip. So you have two elements that could happen that are bad for production. Could get into the part, work hard in the part, or it could come back into the tooling and have premature wear on your carbide. So, as Bryan mentioned, high pressure coolant right at the area on the swarf is key. And that really makes a big difference.
Is this also related to like what does Citizen have? The FLV?
Variable vibration?
Yeah.
Yes.
This is the same thing, controlling the chip and breaking it up, or is that sort of its own?
Well, it's its own thing, and what it is, it's basically almost like a micro. If you ever heard of a drill being peck drilled, you know how you go in and out. Okay,
peck drill.
So picture that like a million times a second. I don't know, it's just something. It's just rapid fire where you don't even see it, don't even feel it, so it just vibrates that chip out of there. It's almost like an interrupted cut. It's creating an interrupted cut.
Right, but that's another thing besides the high pressure.
That's another thing besides the high pressure.
What about type of coolant? Since we're talking about coolant, what about people? Some people like the vegetable oil, or how do you see? I mean, you're seeing cutting, obviously, with cutting tools. How does that affect the quality of the cut? Or is it just more you're worried about the bearings and the other stuff and environment and, what do you guys advise customers on it, or do you have any opinion on it? I'm sure you have an opinion on it.
Well, coolant does numerous things. It helps lubricate the cut, cools the cut zone, and it helps remove chips. So, a lot of companies still use coolant for those reasons. A lot of places in Europe demand dry machining, okay, because of laws, because of trying to dispose of the coolant waste.
Oh, okay.
I can tell you this, in most alloyed steels, coolant concentration is anywhere from 6 to 8%, and on difficult to machine materials, when I say 6 to 8%, it's 6 to 8% of the coolant concentration to water, okay?
Oh, okay.
And then 8 to 10 to 12% coolant concentration on stainless steel, duplex stainless steels, 300 series stainless steels, and even your high temp alloys and some aluminums.
So people buy, and if I understand you correctly, depends on what kind of material they're machining. They'll buy coolant that has a different ratio of water to...
No, typically when they buy coolant, they buy it in 55-gallon barrels.
That's what I was thinking. They're using it for all the machines.
They have a way of mixing that ratio into the coolant tank with water and test that with a refractometer. It's a device to be able to put a drop of the coolant on. You can measure what the percentage of that coolant versus the water ratio is, so you can know exactly where you're at. So a lot of milling now in most materials, except for your super alloys and your duplex stainlesses, are done with dry machining.
Dry machining?
Dry machining. Why? Because a lot of the
you don't need the through...
No, you don't. And I'll tell you why. A lot of the high-speed milling applications like HEM doing side milling, radial chip thinning, and even some feed mill applications where you have axial chip thinning, is when you're in and out of the cut so fast, especially using end mills, you have to generate enough heat to plasticize the material and get the coating at a working temperature to where it forms a gaseous layer on a molecular level to help lubricate the cut. So if you throw coolant on the operation, what it does is the thermal shock. It does not allow the coating to get hot enough, therefore you're going to get quick tool wear. Because all the coating is a thermal barrier.
So that's why they're doing it dry, not just because of the environmental stuff.
No, it's because you want the cutting tool to operate at a certain temperature to get the benefit of the technology.
But you don't want to run into bad chips in that case. So it's got to be a case where you're not going to run into bad chips.
Well, case in point, if you do dry milling, you need air blast. You need some way to help evacuate the chips. Air blast. Okay. Now in turning, most turning is done wet. Okay, because you're continuously in the cut, you're seeing a lot more heat. Okay, you're generating more heat.
It's sustained, as you said, interrupted cut, not sustained in a turn cut. Sustained heat, it builds up, right? So if you notice, Bryan mentioned that you have a lower content and percentage of the content of the coolant in the water. Then you mentioned some of the higher high temp alloys, right? With alloying elements, that insulate heat. So now let's go to the small diameters on the Swiss machine, and guess what they use? Oil.
Yeah.
Right? Very, very.
Well, unless they want to mess up the resale of their machine.
That's true. If they don't care about that, then sometimes, right, exactly right. So why the lubrication is needed so well in those high temp alloys, and also more importantly, the surface speed is so low on those small diameter parts. Listen, on a mill, your surface speed is figured for your grade of carbide with the diameter of the mill because it's rotating, and there's a formula you figure that out, right? But when you're taking a stationary tool and you have a part that's 150 thousandths in diameter, like the needle I discussed, right?
Yeah.
The surface speed is very low. So you better have high lubrication content oil, extreme, that handles that. So there's a few, the environmental impact on that, absolutely, for sure. You have high sulfur content oil, which is used for your stainless steel high temp alloys. And then you have your cheaper, not so much where it's sulfur, but it's a little bit eco-friendly. Okay, but you don't get the same lubrication benefit of the high sulfur content, more expensive oils. But that's why it's used, because of the small diameter in those applications.
And it's better for the machine.
And the machines are designed for it; they're built for it. That water soluble stuff. Which the content you can get rusting going on and things of that nature.
But a milling machine, and I'm not an expert on that, but or just I don't know, some kind of your typical 3-axis CNC lathe or your, VF2, you don't need oil on that.
That's exactly right.
Do you not want? Would oil hurt the machine? I don't know this stuff.
It's unnecessary and it's more expensive. That's why you wouldn't use it. You would use the water soluble.
Reason, absolutely no reason.
No, not no.
It's not going to mess up the bearings or
no. No, there really isn't, and I just think the application calls for it. When you're talking about, and so when you have that, listen, when you have that more expensive lubrication, now what do you want to do with this technology? You want to speed up your process. So if you're spending that money on expensive tooling and you have coolant through holders, and then you have high pressure coolant, which costs money, right? It costs money to put it on a CNC machine. Now you're able to run faster, more productivity. That's how you make money.
I didn't realize that many people ran dry stuff. I mean, I've seen them running some dry stuff here at IMTS. You seem like it was on brass.
Yeah, and so you can see it, but
right,
honestly,
they wanted you to be able to see it
absolutely.
being machined.
We don't see. I wouldn't call it a lot. Would you call it a lot? I don't think it's a lot.
In high speed milling applications, HEM applications, optimized roughing, using radial chip thinning on end mills, I see it quite a bit nationally when I travel the country.
What's quite a bit? 20% of the time.
50-50.
Wow.
So it depends on the material. It depends on the comfort level, too, of the end user. Some people will sacrifice tool life because they like the ability of coolant flushing chips away. It's a mind. It's an adjustment.
You said in Europe that sometimes they have to do it.
Europe, they do a lot of dry machining because of the laws over there with trying to dispose the waste of coolant. So they don't have a choice in some cases over there.
A lot of interesting things learned today. Is there anything I've missed? Or I mean, there's a million things you could teach us. But each of you go individual. What do you have to say to the people of the world?
Well, regarding Iscar's innovation in small diameter milling tools with indexable inserts, you have to ask the question, well, what's the payback? I have to buy a pack of inserts. I have to buy a new cutter body when I can just buy a solid tool. And maybe I'm getting 3 regrinds from a solid tool. Is it really worth the investment? Generally speaking, this is how the math breaks down. If you're using a solid carbide end mill, you get 3 regrinds. You add the price of the tool plus 1/3 of the price of the tool per regrind. You add that up. Then you start adding up what's the cost of the inserts with the cost of a new cutter body. It generally, rule of thumb is you have to buy 20 inserts to replace a premium end mill. When I say a premium end mill, it's design that's application specific for materials and application specific for given given scenarios. Typically, when I say buy 20 inserts, it's to break even on the cutter body, the brand new cutter body that you're putting the inserts in. For a commodity or general purpose end mill brand that we see mostly in the country today, because carbide and milling is, especially end mills, is basically the CNMG of milling. It's become a commodity. No matter what brand you buy, it's generally 30 inserts that you have to purchase in order to break even on the cutter body. So you have to do the math. It has to make sense. You have to have a skilled labor force to be able to take the time and patience to index these inserts. And it's training. It's training from our people to the end user to be able to give them that comfort level.
Michael?
Well, I think that quick change, sharp tooling, submicron grades of carbide, coolant through tooling is essential for success on the types of environments on Swiss machines. Accurate indexing, again, for the labor force, the labor skill that you have. In those environments, typically you have multiple machines running without operators, without machinists. Okay. So, and sometimes you do it lights out during the night. Okay. So in the larger environments, they have robotic arms that replace the parts. It's a different thing. Here, when you have bar feeders on Swiss machines, it's automatically loading the stock, but you want tools to last a long time, but not too long because they're expensive. You want productivity. Okay. And then you want chip control.
But not too long. You want them to last a while, but not too long?
Excuse me, I'm sorry. Well, listen, there is a general rule of thumb about 20 minutes of cut time on a cutting edge, but that can vary depending on the materials you're cutting. There is a general fine line there, okay?
Even if it doesn't wear out, you want to replace it?
Yes, sometimes.
So this is another good tidbit.
Yes, absolutely.
Probably a lot of people don't know
Well,
that.
think about this. In aerospace, customers will index the edge even if it's not worn out because they don't want to jeopardize scrapping that part, that expensive forging, because of tool life. They'd rather just index to a fresh edge so they don't have the potential of killing an expensive component. So
breaking the tool
right.
during that one
during
component.
the cut.
Right.
As if it's like a $100 component.
Right. Or let's say a $10,000 forging. I'd rather index an insert prematurely to keep from scrapping that $10,000 forging. Of course, they measure tool life based on their criteria and their comfort level. Everybody's different.
If you're making a $5 part, are the people going to basically just run the tool until they see it not doing very well?
They're going to run it. They're going to push it a lot longer because then the cost of the tooling starts to outweigh the cost of the part. And if you're going through too much tooling, there's your tipping point. There's your tipping point. So, yeah, it's a good observation. Yeah, it really is interesting. And so when you're looking at that and the quick change environment, when you're looking at longer tool life and chip control, it's all part of more productivity, lights out manufacturing. Here's why. Reshoring. Okay. Again, you still have the labor factor, the cost of labor around the globe. Okay. Our competitors are not here in the United States anymore. They're globally, right? Yeah. So you have that labor. So the differential, our philosophy at Iscar is the labor differential is through using technology, all these ideas we've discussed to reshore the jobs back here in the U.S. so we could run them.
Right. Although I'm sure you sell all over the world anyways.
Oh, listen, absolutely. No question about it. But it's the competition that drives the cost of components for whatever industry we're talking about down. And that's good for the consumer. That's what you want. That's healthy, competitiveness right there. So technology, and I think technology and buying it and the cost of it is much more embraced because America was faced with a labor differential. Okay, that was staring America in the face. We had the technology. We had the know-how, but we needed to really be aggressive so we could reshore that and bring it in. So how do you do that? You do it with automation. You do it with lights-out manufacturing, right? Instead of having a person at every machine. It's a sad story for maybe the labor market and the number of bodies, but in these days, it's hard to find people anyway.
Yes.
So that dynamic too is driving the technology of it, right? Robotics and things of that nature.
Very good. Very good. I just one more question that I like to ask people I interview. What's one thing that you learned last week? It doesn't have to be anything about machining. It could be something you read, watched on TV, just heard somewhere?
I would say listen more.
Yeah,
Listen.
There was a certain thing that happened that made you want to listen more?
Yeah. It's amazing how the human brain is and relationships, and you take more time to listen instead of talking, you understand a lot more. Because none of us walk on water.
Okay. Very good. Michael, is there anything specific that you just learned recently that struck you? It could just be like, some piece of trivia or whatever.
Well,
something you found interesting.
I think I was more reminded than something that I learned cold. I think it was just is when we go into the field in a professional sense, if we're looking at helping and not selling, really, if you're looking at helping customers be successful, right? And we mentioned about, well, if it lasts longer, you're not going to sell as much, or near net shape parts. Doesn't that hurt us? And that's true. It's
I'm
true.
Just messing with you.
No, it's okay. It wasn't a bad thing, but it's a good observation. And so it's like it's almost like, with all due respect, it's somebody that would be in school would be go, well, why? It's an obvious question. Why would you do that? You're in the sales business, right? Well, the bigger picture is looking.
The people want the VCRs to break, so then you'll buy another one. I mean, that's business 101. Right?
That's true, but the world is your oyster. So if you become a resource and not just a place to buy tools, that's when you make a difference in the world.